So in terms of an outline, I'll briefly mention about energy demand and why that is creating a lot of attention. Then of course I'll tell you briefly about solar energy research in our lab, a couple of slides, but then focus on some consideration for photovoltaic devices and how our aerosol techniques can really enable meet some of those design considerations. And of course I'll end the talk with these different sensitizers, and won't have too much time maybe to get into detail, but give you a snapshot of these different biological sensitizers that we are working with. Of course energy, this audience, I don't need to address that, but if you look historically, interest came and went. She mentioned I got my degrees in the 80s. I came all charged up to work on solar energy as a graduate student, and then of course all the funding was pulled in that sector, and I instead became an aerosol scientist. So it's coming all the way around. I always related to the energy sector in terms of work, but they come and go, and it has resurfaced now, and but it's very different in terms of the problems are still the same, but it's very different in terms of the attention it's getting. One is this carbon dioxide issue. We really have to overcome that. There's no question about it now as we move on. There are many other things that are listed. I call them elements of the energy equation. Fuel economics, reserves, how much do I have remaining, energy security, and then of course these environmental connectivity. Another very important aspect is the linkage to these developing nations around the globe, large populations, mainly in Asia, and these are large distributed populations in some sense that is off the grid, and there's a big clamoring to use energy. So if I look at that, the population again in these nations are going up. Of course there's some flattening. If you look at the curves where we are, the industrial countries, there's not much growth in what we use, but even if we do that, it's not going to make an impact just in terms of the number of people, and you know the population still is expected to double and so forth. And correlated to this is the energy use. So I like to use, of course I come from an engineering background, we love numbers always, so we use 14 terawatts. The lamp above your head might be just 100 watts. So this is a humongous number. About 16 terawatts more. So you know, as the population doubles, our energy consumption is also going to double in some sense. Of course we want to be as efficient as possible, we don't want to be as wasteful, but it is still going to go up. And I just want to place this in perspective. What does this mean? One way of looking at it is that 16,000 gigawatts, and if you look at a modern power plant, I don't know how many of you have seen an electricity producing power plant, again huge structures, most of them based on coal, but if I build a new plant today, it's about 1 gigawatt. So if I want to meet all of this as electrical energy or as electricity, which is a common form, I need 16,000 new power plants. Of course we have 40 years, these are the young students in the audience, your entire lifetime to work on it, and that is 400 every year. We know how many days there are in a year, so it's quite a bit of a challenge. I have to build one of these huge structures every day literally to meet these demands over the next 40 years. We definitely need technological breakthroughs. I can't build one every day. I'm not even looking at the environmental footprint. And then I look at the sun beaming down on this planet, about 174,000 terawatts. These numbers vary depending on where you are and things like that. Quite a bit of it is harvested by biological systems on our planet. They do it extremely slowly, but compared to what we need, really this is just a small fraction. So there's a lot to be done. That doesn't mean that solar energy is the solution. There are many challenges, and I'll address some of that. But nonetheless, my last slide on energy, in a general sense, it's going to be a mixed bag. It's not solar or coal or nuclear. It's going to be everything. How do I make a decision? What do I use? We need to do life history calculations. So these are accountants. Next week you heard an economist is going to come talk to you folks. They are good at accounting for dollars and flows. There are socio-cultural dimensions. I might just love a particular source for whatever reason, or I might have no choice. And it's going to be a mixed bag of all of this. And then on the right hand side, we all have to take care of all these other issues too, equally important, and these all go into the decision making process. Okay, so having said this, let me now switch gears and tell you how a tiny solar cell works. On this campus, there are only 2 locations, one on the library building and one where we come from, Bravo Hall. These are made out of silicon. So let's just look at this. A solar cell has something like a N-type semiconductor and a P-type semiconductor. They are just sandwiched together. Then there's a little contact. I can light up a bulb or use the electrical energy that is produced. So when I have some photons impinge on these semiconductors, it creates, of course, the photon has to be absorbed by this type of material. So the choice of material is important. It creates an electron hole pair, and then of course there is a certain bias that is created, and I'll go into that a little more later, and that causes these electrons and holes to separate, and then of course the electron actually flows through and might then come back and recombine, and this cycle just continues. The next photon comes in and we just continue this process. Of course, we want the electrons to be pulled out very effectively, so it has got to do a lot with the structure of the semiconductor, how it looks and so forth, and I'll talk about that. Most of the conventional solar cells or whatever I buy in the market today, other than a few next generation type photovoltaic devices, are made out of silicon, and again there are a whole bunch of steps that dictate the price. They are still made using many similar techniques that we use to make electronic devices. So my little cell phone has a lot of chips, and that keeps the cost high. People are now looking at it, trying to modify these pathways, each different pathway. We do that in our own group and so forth. So you start with low purity silicon. It's called metallurgical grade silicon. You can go dig up some sand, silica, and then convert it to silicon. So it's quite abundant in that sense, but this is low grade. Then I have to get polysilicon, which is a purer form than this metallurgical grade, but it's still polycrystalline. It's not single crystalline. I go through number of steps to make it single crystalline silicon, which we of course need for our semiconductor devices, electronic devices. Or I could use low grade silicon, which might be less expensive but not as effective as single crystal silicon. I want to make a wafer, I want to make a cell. Every path, every step there is some waste, and we need to address it if I want to bring the cost down. And because of this, this is not very prevalent all over, though it should be. Of course, prices of silicon, it's a market based thing. Someone might dump into the market and reduce the cost, and that has happened, which has other effects. Again, I'm not an expert on that, but this is how you make it. I'm not going to talk about silicon, but I'm going to sort of address some of these challenges. So one is solar energy is intermittent, right? I want my lights on a day like this, very little beaming down, at least on the roof of this building maybe due to the clouds today. So I might need to store it. I could couple it to high efficiency batteries, or I could promote certain chemistry, and all of this is to be looked upon holistically. Then can I replace silicon based? While I say replace, maybe the right word is modify to bring the cost down. Can I use different materials because cheaper devices would be easier to market and deploy, maybe, and so forth. Or I modify the silicon fabrication process, as I indicated, to reduce the waste. Again, I won't go into that today. We want to improve the overall efficiency of the device. So I'll briefly touch upon some of these things. Again, solar energy has a large footprint if I want to use it. The reason why we use coal so effectively today is coal is a very dense fuel. I just dig up a little bit of coal and I can generate large amounts of energy. With solar energy, I need to have a large footprint. So whenever I can improve the efficiency, that of course reduces the cost, but also makes it more viable, because the roof area that I have is just limited to, let's say, this building. I don't want to cover up the entire campus. So this efficiency is very important. So this is what we do in our lab. Again, a busy slide, I'm not going to go into it. We look at energy applications. I'm going to talk about some photovoltaic devices, and maybe more so in this region, and some of our single crystal structures that we synthesize. Of course, there are many environmental applications. Even promoting chemistry, you can convert CO2 back by using solar energy. This is a very energy intensive process. If this is indeed the problem, let's also begin to address it. So you can see these fields are not different in any ways, but they're all interconnected, and one could use all of these. So you can look up our website and learn more about this. So let me just cover some of the important aspects for these semiconductor devices. So one, as I indicated, and I already covered some of this, the choice of the material. It's based on the optical absorption threshold. I'm going to talk about oxide-based semiconductors. So the limitations are therein. The light absorption depth, how thick do I make my solar cell, right? I want to absorb all the light that is incident on it. This dictates the dimensions. Obviously, I want to use the least amount of material to keep my costs down. Then this concept of a space charge layer, I'm not going to get into it too much, but just indicate qualitatively to you. And this has to do with the shape of the structure that I'm going to make for my PV device. And then of course the electron mobility and diffusion length, which also depends on the shape, the crystal structure, and things like that. So let's just pick on these. The optical spectrum, or the solar spectrum, is shown here. This is the wavelength, this is proportional to the intensity, and you can see the band structure of many semiconducting oxides that are listed here, and I've just picked TiO2. This is a common material used. It's very stable, it's inert, it has a band gap of 3.2 eV. That's quite a large band gap. So only the photons that have energies greater than this would be effective if this was my material with which the device was made. So you can see only a small fraction of the incident irradiation could be harvested, right? So the light absorption threshold, silicon is somewhere, it has a shorter band gap than TiO2 is somewhere here. But again, you can see that there's a large spectrum or the large wavelengths, the longer wavelengths are really not harvested in most of the semiconducting devices. So I need to address that somehow. So that's the first thing, is how do I choose my material, or if I choose it, can I do something to enhance the light absorption over a broader spectrum. So that's one thing we keep in mind. The other thing is how thick should this material be, or how thick should my device be. Of course, you don't want the light to just come in and get through. And a simple Beer-Lambert's law expression could then, using the absorption coefficient, be used to calculate what we call an absorption depth. So I just use as a characteristic length 1 over alpha, the absorption coefficient, or the inverse of the absorption coefficient. This is of course a function of the wavelength, so you can do these calculations, and you can see that this would guide the thickness of the film that I require. The greater or the higher the absorption coefficient, the thinner the layer can be. So iron oxide is a good absorber in the visible ranges, so it's could be relatively thin, and you can see that for a few other semiconducting materials. So that's another characteristic I keep in mind. And then the space charge layer, the concept of the space charge layer. So if you look at all these band and energy levels, and here I just show a certain redox potential, and because of this band bending that takes place at equilibrium, you want the Fermi level to sort of become equal to the redox levels, and because of that there is a certain band bending, and this is very important because this region is where the electrons and holes or the positive charges would separate, and that's what I want. If you recall the picture I showed you, I want the electrons to be pulled out, I want a separation, I don't want them to recombine or be all tied up together. So this separation takes place in something called the space charge layer, and of course one can do these calculations. I'm not going to get into all of this, and you can relate it to the characteristics of the material, but we just say that there is a certain space charge thickness W that is something that is important in my structure, right? And the length could be L, but it's only this W, this certain layer, that is important in terms of the separation. Then is the electron diffusion length. So once I separate it out, there is a certain characteristic diffusion length, and that depends on a diffusion coefficient times a certain lifetime, and of course the square root of that. These are all characteristic dimensions. I can calculate these by doing experiments. There are ways to do electron lifetime measurements by just measuring the open circuit voltage decay rate. You can also estimate the diffusion coefficients. It depends on the, again, the material and the transport characteristics, and one can get then an estimate of this diffusion length. So again, remember the space charge layer and then this electron diffusion length, and this is just illustration of showing you that. So again, this might be important, but if the electron can only diffuse a certain distance before it's lost or recombined, it's of no use to us. So we need to match this out. So I put all of this together. So a flat structure like this, the absorption depth, of course I need to exceed that, or at least have that, to make sure my photons are absorbed, right? But then within that, this layer is important, and I just discussed this layer. Now how do I take this and make it more effective? So this is why I'm justifying a one-dimensional morphology or a one-dimensional structure, and why it is recommended. So the space charge layer could be distributed along this long column, and then I could have a significant region where the electron hole pairs are generated or separated, right? And then the lifetime is sufficient. This length is now sufficient to separate out the carrier by moving it out of this structure, right? So these three layers overlap. So a structure like this could be important. Now this is better. You could also have a granular structure. I could have a small nanoparticle, semiconducting oxide nanoparticle, but then the electron has to hop from one granule to the other granule, and this then creates a resistance or also affects transport, or what we call a grain boundary resistance. So a structure like this, which is a single crystal, would not offer that resistance and allow the electron to be pulled out to the electrode or to wherever you want to then drive it through your load. Okay, so these things. Now how do I bring, this is where I now want to address how aerosol science might play a little bit of a role. The synthesis of structures becomes extremely important. How do I really make these structures, do it in a way that I can fabricate large quantities and large amounts in a low cost manner? And I'm going to describe an aerosol route. Now you're hearing this word aerosol quite often, so let me say define what is an aerosol. So if I want to define, and I see some aerosol experts here, so I'll look on that side of the room. You are going to do a Google search. These days images, search with images are important, so this is what comes up, and this is true, right? Now some of you might enjoy these shoes. I of course like my soles to be soft. So this is also a structure, but this is nothing to do with the aerosols I'm going to talk about. Neither has it got to do with these spray cans and so forth. And these are searches from Google. So it is a gaseous suspension of fine particles, nothing but a fine particle that is suspended in some kind of a gas. It has a Greek origin. The word has a Greek origin. It's a noun. So if I use the term aerosol particle, you can pull me up. Not the right way to piggyback two nouns, but people often use that, or aerosol nanoparticle, but it is indeed a noun by itself. Okay, so knowing what an aerosol is, in our group we try to understand the formation of clusters. We start from the molecular state. So a stable cluster of molecules is a particle to us, right? How do I create these particles? It's great if I could start from the molecular state or the vapor state. Anytime I want to get into a vapor state, you know, high temperatures are good. It helps enables get into the vapor state. By the way, the water cycle that's happening outside today is also an aerosol process. So our very existence is due to a successful or a natural aerosol pathway that's taking place. That happens under more ambient conditions. So you don't really need, it also depends on the material. So from the molecular state, I want to create these stable clusters, and then of course I can create agglomerates and so forth. And the applications, it's a fascinating field. Oftentimes the term bad aerosols are used because some of these are unwanted particles when you drive your car around, or when I burn coal. You know, this in fact is something that comes out of a coal-fired combustor, very complex looking structure with porous kind of structure, and this could be filled up with all kinds of toxic constituents. This itself is quite harmful if we inhale it. There are also these volatile metals that come out of coal combustors, more spherical in shape and more dense, but extremely problematic. But the same pathway can be used. We try to understand these pathways, so I want to prevent the release into the environment. But the same pathway could be used to engineer and make nanoparticles, right? Now very uniformly controlled, and it all has to do with these pathways. And today, of course, I'm going to talk about making solar cells and the good stuff. So of course, I have to rely on aerosol phenomena and aerosol physics. So here, these are the scales over which I might have to deal with this problem. Start with the molecular scale, nucleation. So this initial step is known as nucleation, moving from a molecular state to a cluster state, and extremely complex in high temperature environments. Until today, we don't understand this very well from a theoretical perspective. Experimentally, we are designing instruments to really measure this out and map these rates out. Then condensation, the molecules could really condense on a particle, existing particle, and this would result in growth. Two particles could collide, and you can see that I have an agglomerated structure. Now I'm dealing with particle-particle collisions, so it could take place over all these different scales. This could be a time scale, this could be a length scale, you can choose. And then once I have a structure like this, it might collapse back. It's like it's in a high temperature environment. So the preferred shape is a sphere, and it might really collapse back into a spherical structure. And this condensational growth was shown here. So the size changes, the composition can change, all kinds of things can change. The crystallinity can change. So we want to understand this to control our growth processes. So I'm going to show you some systems where I use it to make now those one-dimensional structures, right? So I take a flame, I bring in a precursor, and these are all metal organic precursors, and depending on what I control out here, I can get different morphologies. We call this morphologies. So this is an extremely high surface area structure, and if I'm promoting localized chemistry, as I told you, this may be good enough. But if I want to pull the electrons all the way to the substrate, this is not good. because there is a grain boundary resistance, right? So I can then have an intermediate structure, and then eventually if this structure sinters out, or as it's growing it sinters out, and I have one-dimensional crystal growth, I have these very elegant looking columnar morphology which has a single crystal and would be very effective and in terms of the electronic properties. The surface area is not as high as this. I want a high surface area, as I indicated, to harvest more sunlight, but this might be a good compromise. Okay, so we'll see that. Now, how do you really understand why I get this columnar morphology compared to a granular one? Then this has got to do with all kinds of characteristic times. So one is the residence time. So right from here to here, the transport from here to here, there is a certain time that I have available to me. There is a precursor entering this high temperature zone. So this is a chemical reaction, just simple chemical kinetics, which allows me to see the conversion and create the oxide. I'm bringing in an organometallic. I don't want to deposit that. I really want to deposit the oxide. So I want it to chemically react. Then there's a collision time. Once I react and form particles or nucleate them, I want them to collide, and there's a collision time, and then there's a sintering time. Okay, so a balance of all of this and controlling it, and I can control it by controlling the flow rate, I can control the temperature, I can control the substrate temperature, and again I'm not getting into too much detail. Details are available in earlier publications. I can do a very detailed simulation by tracking each single particle and see how they grow, and again depending on, so let me just tell you, if the arrival time is much larger than the sintering time, so a particle is coming down in a certain amount of time, right? If that time is much larger than the sintering time, then I'm going to get a granular structure. This is in the gas phase, by the way, right? And of course, if the two are equal, then I'm going to get a dense, or if this is much smaller than the sintering time, I'm going to get a dense structure, and then an intermediate balance would give me a columnar structure. So we can play with this, control my process, and get any desired morphology. I also modify the process. We call it an aerosol CVD technique. Flames are good, but sometimes difficult to control. This is like a chemical vapor deposition process where I heat the substrate, right? I heat the substrate and then control all that is happening. Again, it's a play with all these different time constants, and I won't get into that here, but I have the same kind of thing. So if the residence time is much less than the reaction time, right? By the time I move from here to here, this reaction time is so large, and it all depends on what I choose, what the temperature is. I'm going to just react it on the substrate and get a smooth film. Okay. On the other hand, if the residence time is much greater than the reaction time, I'm going to form particles, and if the particles grow to be large enough, I'm going to get a granular film, because large particles sinter at a rather slow rate. On the other hand, if I have the right intermediate conditions, I see that small particles deposit here and they sinter out, and then the single crystal structures grow, and I get this kind of a columnar structure. So this is a ACVD process and I can do it with different precursors and so forth. But something rather interesting begins to happen. I want these to grow to a sufficient length so I can really use it effectively as a device, and because of the heat transfer, then the upper regions start cooling down, because this is hot now and this starts cooling down, and those characteristic times change. Again, I can do heat transfer calculations. I'm not going into all those in detail, and I compare the different characteristic times, the sintering time with the arriving time and so forth, and you can see that I reach a condition where this is now cool enough that this particle is not going to sinter with this. It's also a small particle sintering with a relatively large structure, so this becomes a slow process. So the next arriving, before this can sinter out, the next particle has already arrived there, and you can see then, in fact it's got cut off, but you can see that if the sintering time is much smaller than the arriving time, it's going to become one big blob. If it is not, it's going to start growing there, and you begin to see these structures. Again, I'll just walk you through this. This is the precursor coming. I'm forming my single crystal structures. I can do it for about 60 minutes, but then it's become long enough, it cools down, and I start growing branches. So instead of growing single columns, I can get, you can't see this too well, but maybe the next picture, you can see I can get these branched structures. So we can really literally play with the different morphologies. You also want all these crystals well aligned. You have certain preferred crystal structures that you want to grow. You don't want multiple crystal phases, so you can control all of this in great detail and then get really interesting features. You can grow a forest of columns, you can grow branch trees and all kinds of things, and each of these might have a different application. So what do I do with this? I take this, I put it into a photo splitting cell, as we call it. Of course, these days we also have 3 electrode systems. I shine some light, and I really want to see the performance, how effective it is. So I can make these different morphologies, and I want to study the effectiveness of these, and I'll just show you some results. Here is the water splitting photocurrent. So I put it into this device and shine light, and I can measure the photocurrents, and I plot this as a function of film thickness, and you can see the columnar films are much more effective than the granular films for the reasons that I quoted. And this is an actual test of these different structures, and of course these solid films are the least effective. The granular films at least are partially effective, but the columnar ones are more. And there is an optimal thickness, because once I go beyond a certain thickness, the electron has to traverse a greater length and could be lost. So as I grow these films to be thicker and thicker, they of course harvest more sunlight, but most of the electrons are lost. Okay, so we can do studies like that to find out the effectiveness. I can go and do some lifetime measurements, as I indicated, by just tracking the open circuit voltage as a function of time, and you can see that the electron lifetime in a columnar film is much greater than that in a granular structured film. Okay, so that then of course just gives me additional support for what we have measured in a bulk way, and we can then fine tune these morphologies and so forth to be the most effective. Okay, I want to, in the remaining time, talk about some sensitizers, and I need to do that to improve light absorption. TiO2 is great, it's easy for me to make, it's stable, it's a low cost material, but the efficiencies overall could be rather low, especially in the visible spectrum, for the reason I showed you. The band gap is quite broad. So how do I improve light absorption, and of course then the overall efficiency? And again, this shows it. This is the IPCE, it's an overall efficiency, and this is AM 1.5, air mass 1.5 irradiation as a function of wavelength. This is a standard that we typically use in the lab. So we have these solar simulators that you can test these devices, and you see that this TiO2 film is of course effective only at the low wavelengths, and by the time you come here it has zero efficiency, right? So it's totally ineffective, and you're just wasting most of this irradiation. If you could harvest it, that's great. So people have, Gretzel is the first to have designed what is known as a dye sensitized solar cell. The mechanistic description is out here. Now you don't directly absorb in the TiO2, but I mean you could absorb directly in the TiO2 depending on the wavelength, but most of the visible spectrum you would absorb in something called a dye, and these are some artificial dyes made out of ruthenium, very expensive, but you absorb it, it excites the electron to an upper state when it absorbs visible light, and then if you can match these energy levels, if this is higher than what is available in the TiO2 layer, you could inject it into the TiO2 and then go through and have your redox mediation and continue this cycle. So sensitizers are very effective. You can absorb more sunlight in the visible spectrum, and here are our columnar structures just seen by the eye, and then when you coat it with the dye, and you can see the dye molecules are well distributed. So even for a conventional dye system, this is quite nice in terms of the morphology, and people are preferring one-dimensional type structures. You can engineer the band gap. I won't talk about all this. Let's just focus on sensitizers. I won't even talk about quantum dots, but let me quickly go into these other two in the remainder of the time. Now we bring in aerosol methods again to play a role, and this is of course with quantum dots. Whenever I want to link a sensitizer to my TiO2, people have to use some additional things called linker molecules, and those, anything that you add is going to add a resistance or going to do something to your electrons which would be lost. Okay, so if I have techniques by which I could deposit these directly and keep them to, you know, stick to the TiO2 layer, that's great, right? So again, using some of these aerosol techniques by charging some of these particles and driving them in a electrical field, we can really bring them to impact and stick to the TiO2, and once it arrives on the surface, van der Waals forces are strong enough to keep them there. So we've done that with quantum dots. As I said, I'll skip that for now, but let me talk about antenna complexes. Of course, there are experts. This is Bob Blankenship's diagram of all kinds of antennas. So these natural systems have these structures which harvest sunlight and funnel them onto the reaction center. Okay, so I want to know is, can I take some of these components and actually make devices just like I described earlier. So I'll describe another device we have in the lab. These are basically in-flight measurement devices. I need to know the size, I need to know the charge on these particles as they are flying around. I don't want to be collecting them, going to an electron microscope, doing spectroscopy later. I mean, we could do that, but it takes a large amount of time. I want to quickly be measuring this. So we have devices like this called differential mobility analyzers. I bring in a particle with a certain charge, and based on the charge to size ratio, I can deposit them at different parts. If it has the right size that I tune in, I can pull it out and I get particles all of the same electrical mobility, right? So this is an electrical mobility measurement. If I know the charge, I can pull them all out of a certain size, I can count them, and I can change this voltage and get the entire size distribution. And this is now of course a standard instrument, and I can now spray out my chlorosome structures. The first one, assembled structures. This is a DLS measurement. Again, this is offline. I have it in a suspension. This is done by also a type of electrical mobility measurement, but this is in flight now. So I electrospray it, I can get singlets, and I can get a very sharp distribution. Sometimes I get doublets and so forth, so there is some interpretation. I might have residues. In fact, I can tell the purity of the samples that Greg would provide the students by doing some of these measurements. Now we want to learn from nature. We want to take this and couple it with a TiO2 structure, and you can see that these structures are basically assembled pigments. The pigments are of different types naturally occurring. There is a certain base plate that holds it together, and then the reaction center. Now I want to use an artificial reaction center because I want to take these entities, electrospray them and get it on to the reaction center which is on my surface. Now why would I do something like this? I can absorb in longer wavelengths, as I said, so that's the goal. Eventually I want to, you know, absorb at those frequencies which are longer wavelength, and I'm harvesting more of the visible spectrum. So we can take these complexes and couple it and create devices. So we do this with an electrospray. Now this is the only way you can actually assemble it. I can take a bunch of chlorosomes and dip coat it and hope that it sticks. Firstly, it will all be clumped and not be distributed as uniformly maybe as I have indicated in this cartoon. And secondly, the dyes are water soluble many times or not water soluble, So the chlorosome I want to be in an aqueous medium, but this one it's not sort of compatible. So how do I get both of them on together? So the only way is by a sequential electrospray type technique. Again, electrospray is an aerosol generating methodology. Here I'm not forming from the molecular state. I already have particles in a suspension. All I'm doing is aerosolizing it, putting a certain charge, and then moving it in an electrical field. And you can see that I do it with the dye and then adding these chlorosome structures. The absorption clearly shows that I have some of these deposited on my films. You also get, in terms of crude measurements, significant increase in the photocurrents, again in the visible regions of the spectrum. These are of course very preliminary results. We are trying to do more and more with this. So we have made biohybrid solar cell devices which really are much more effective, at least just compared to the TiO2 and dye, and again in the wavelengths that are of interest, pushing it to the longer wavelengths. Another student, Ray Henson, working with several others, has taken an entire structure now. I see Haijun is here. He provides these PS1, which is the entire entity now. It's not just the antenna structure with a base plate, but this entire thing with the reaction center. And many people are trying to create these hybrid devices, but the ability to aerosolize, to get singlets in these droplets, controlling the size and so forth, allows us to get photocurrents which are much greater compared to just the TiO2 layer. And of course I can use different light frequencies just to map out these photocurrents and see how they work and so forth. But the key is electrospray enabled deposition, controlling the agglomerate size, the orientation now, because this is an entire entity. It has to inject the electron directly into the TiO2. The orientation becomes very critical and so forth. And this is the currents that he measures is far greater than what has been reported by others, because they again have to use linker molecules to get on the PS1 to stick to the semiconducting materials. Then you want to go artificial. Getting these from Blankenship's lab won't allow me to build devices which last 30 years. I want to compete with silicon, so I want to eventually rely on synthetic organic chemists who can make these different structures, and these are just analogs. Again, I won't go into details. There are all kinds of different analogs. They can have the center zinc, they can remove it, they can do all kinds of different things, but these pigmentary molecules then have to assemble to be effective, right? Only, and of course these are different absorption spectra of these different analogs. Let's skim that. There are certain candidates that are good for being assembled. If you remember the chlorosome, I didn't point out the green pigment, they're all naturally assembled in these living cells or these living structures. Here I have to do that artificially because they can make the monomers, but I have to assemble it, right? So how do I really assemble it? Most people use solvent based methods. Firstly, I can do that. So I put them into a beaker, I do some shake and, there's no baking here, there's only shaking, adding certain solvents, and I get these nice assembled pigments in solution. How do I get it onto my substrate? Okay, I can electrospray this out and get it on. That's one possibility. Many times I have to add surfactants to make this happen or not happen or control it. That then brings in impurities. So we want to also promote now, this is a surfactant based method, an aerosol based self assembly with no additives, better control, and eventually I want to be able to get multiple layers out. So Vivek here and Jerry, they're doing a lot of work, some measuring the kinetics of assembly, some doing this electrospray assembly. So you start with the monomers, I can control this droplet size, I can control the charge, and you can see that this solvent eventually evaporates. Of course, this is judicious choice of the solvent. I could add two solvents and the volatile solvent will get out, and then the next one will really promote assembly. I could do that. I can study all of these. So the evaporation time is important. Again, the characteristic time comparisons are so critical of different kinds, which allow us to design these processes. The droplet size is critical, and this is an equation for the droplet size, because eventually I want to create droplets of known size, but then I want to control the evaporation time, the self-assembly time. This is where the diffusion maybe, or the nucleation, we are still trying to grapple with the kinetics here. And then eventually the charge transfer and the orientation, we want to even understand that. So this allows us to do that much more effectively in flight. Firstly, it's a single step, it allows us to do that and also deposit it. And this just shows that these assembled structures have are indicated by a red shift in the absorption spectrum. So these are the monomers, these are the various concentrations. You can play with the concentration, which will then control the kinetics of self-assembly and so forth. Here I just show you the effect of charge. I can change the charge on the droplet, right, by just switching the polarity. So you can see that if these monomers carry a positive charge, having a surface charge to be positive will push them towards the center and force them to assemble. If I put a negative charge, it's going to keep them towards the outer surface and maybe prevent assembly, and eventually it will evaporate, but you will get a randomization of agglomerate that is created and not a neatly assembled structure. And we actually show that by doing these experiments, and again you're doing these to better understand these processes and so forth. So one can control all of this and play with these and so forth. So this then comes to my last slide. We are delighted to be in PARC, which really allows us to get these artificial analogs from collaborators, and then Dewey Holton's group which also are very interested in the energy transfer and the spectroscopy, and of course the Blankenship lab that I referred to. And you can see that by taking these natural systems, we can make biohybrids, right? We can learn from there. We can eventually then go to biomimetic type structures, people who make these analogs, and the goal of course is to improve the overall efficiency. I see there are 5 minutes left. Maybe I should stop, and if there are any questions, I'll be happy to answer them. Okay, so thanks for your attention. No questions, either too clear or too fast. Okay. If there's no questions, thanks, right? Thank you for coming. Yeah. Yeah, there's a question.
On my mind, because today Edward Young, one of the chiefs of intellectual ventures, is speaking here.
Yes.
I was wondering what kind of role intellectual property plays in the use of technologies like this. How does it help? How does it hinder in kind of using this in a commercial?
Okay. Of course, our primary mission here is to train bright people like you folks to go out and then make the money. And we continue with the next batch. But again, there are a lot of faculty members who pay attention to intellectual property, and we do too, right? So if you come up with novel methods, so for example, the growth of those one-dimensional structures that I indicated, it was in some sense invented in our lab. We filed a patent and we hold a patent for that. So the university helps us with disclosing our invention. We disclose to them, which protects it, and then if it's worth something, they would try to get a patent for it. And then that's of course the first step. Someone has to be interested in your patent. So there are two ways of doing it. A bright student working with me could go spin off a company, and we try to help them, correct? Or another larger company or an established corporation might come and license our technology. So there are many faculty who do this. We of course still do basic research. So it's the, as I really meant it, training the student is more important to us, publishing is more important. Again, it varies. I can speak for myself, right? But if there's something fabulous, of course we want to protect it. And certain things get picked up and used. Right now there's a bunch of undergraduates who formed a company and they're looking at some technologies not related to this, but different, and trying to scale it up and commercialize it. Now, so the university is encouraging it, and that's happening more and more. I don't know if I'm answering your question. So the chancellor is very keen on growing this more. So if you look at a school like MIT, they are heavily into it. There's so many spin-offs, or the Silicon Valley, right? Stanford. So there's no reason why we couldn't be. So we need, of course, an infrastructure, a certain ecosystem around us. And I think St. Louis is ideal to be an ecosystem for energy and environmental technologies. Maybe we should step up and do it here, right? So through ICAS, through groups like PARC, through many of the larger grants that are coming in. Did I answer your question? Intellectual Ventures is a company, again, nothing against them. They come and look for these patents, they come sniffing, and they take it off, license it, and then they try to commercialize it. So I think it's more of a business venture. It's their approach, whereas our faculty might directly work with companies that are interested. Yeah, but it's all of the above. Good. Okay. I didn't repeat the question. Maybe I should after answering. So he asked about intellectual property with these technologies. Yeah. Good. Thanks. Yeah.